everyone. It's great to see so many familiar faces and some new faces. My name is Jenny Sabin, and I am the Weisenberger Professor of Architecture in the Department of Architecture, housed within the College of Architecture, Art, and Planning. And I'm also co-leading a really fantastic faculty task force that is focused on design and technology initiatives across our campuses, both here in Ithaca and also at Cornell Tech and Weill Cornell Medicine. And it's my sincere pleasure to welcome Itai Cohen. But before I introduce Professor Itai Cohen, a little bit about this inaugural series, which is titled with the question, what is design plus tech? This inaugural university-wide lecture series explores design research, technological innovation, scholarship, and collaboration across disciplinary boundaries in both science, engineering, and design. The series is represented by a network of faculty from across AAP, CHE, engineering, CIS, arts and sciences, as well as faculty at Cornell Tech. In an era where we are witnessing one of the biggest paradigm shifts in the conceptualization and creation of our environments, objects, and interfaces, this series will present research and projects on topics at the intersection of design and emerging technologies to understand and discuss their impact upon industry, practice, new knowledge, and pedagogy in a changing world. This spring, we will have 4 lectures, one happening each month, and the schedule and listed times may be found on the AAP events website, and I'll post that link into the chat so you can download that to your calendars. And it will continue into the fall, so watch this space. We have some amazing speakers lined up. My colleague, Professor Itai Cohen. Cohen received his BS in physics from the University of California at Los Angeles and his PhD in physics from the University of Chicago. Following his graduate studies, he was a postdoctoral fellow in physics and the Division of Engineering and Applied Science at Harvard University. In 2005, he joined Cornell and is currently a professor of physics. Professor Cohen is an NSF Career Grant recipient. He is a fellow of the American Physical Society and has served as a Feinberg and Bragnitzi Fellow in 2012 and the Rossi and Max Farron Visiting Professor in 2021 at the Weizmann Institute. He is also slated to be the Van der Waals Visiting Professor at the University of Amsterdam in 2022. I'm very jealous. He has published over 110 research articles, given nearly 300 invited seminars, colloquia, and conference presentations. You have one more to add with this evening, and co-authored the book, Finding Your Research Voice, Storytelling and Theater Skills for Bringing Your Presentation to Life. His work has been covered by various news outlets ranging from the BBC to NPR and the New York Times. So please join me in welcoming Itai Cohen. I'm super excited about this talk. I think your work is just absolutely amazing and spans multiple disciplines and certainly engages creative design practices as they meet technological innovation. So Itai, I will pass it to you.
Thanks, Jenny. Yeah, it's a pleasure to be here, and it's been really fun to learn about all the activity going on campus at this intersection of design and technology. And today I want to tell a little bit of a story about bringing physics to the fold. And I'm going to try to do something a little bit different from my normal science talks and really focus on the aspects of design and sort of keep it at a high level where I think you can get the overall ideas that we're trying to bring to the field here without getting caught up too much in the jargon. That being said, if there are any questions, please put them in the chat. And Jenny, if you would be so kind as to monitor that and interrupt me if there are any questions, that would be great.
Yes, definitely. And we'll have some time at the end of the lecture as well.
Yeah, terrific. Okay, so right away, I'm showing you some of the ideas that I have in mind here. We're going to be talking a little bit about origami and the contributions that we've been trying to make to this field. And if you're like me, when I started, this is basically your conception of origami. I could maybe fold this kind of crane, but origami now has evolved to the point where people can fold curved creases. People can make very beautiful tessellated patterns that are quite complex. They can make curved surfaces out of straight folds. And in this particular case, a snake that's wrapping around a scorpion, this is a single sheet of paper, two sides, one green and one orange, that was sculpted into this phenomenal piece. And so origami as an art form has become quite sophisticated, and it may not surprise you to know that it's already found its way into various uses in architecture. So in this case, as a door that beautifully swings shut and can be opened. Of course, in satellite technology, origami has been used to pack structures into very confined spaces, transport them, and then open them up in very reproducible ways for satellites. Now, today, what I want to do is address one of the amazing questions that was posed by Feynman during his lecture, There's Plenty of Room at the Bottom. And in this lecture, this is way back in 1959, Feynman predicted the miniaturization of information technology, and that's been brought about primarily through Moore's law. Our computer chips are now packing millions, if not billions, of transistors within them. And in that same lecture, Feynman also talked about the miniaturization of machines. And while the electronics portion of that miniaturization, I think, has borne great fruit over the intervening years, the mechanics portion, how do you shrink down mechanics in machines? That part, I think, still has a way to go. And this is what I want to address in this lecture. Now, in particular, the electronics portion, right, the part that's driving these machines, that we can already make small. And just as a way to show that, I'm showing you here devices that were made by my colleagues, Al Molnar and Paul McEwen. And these devices are basically little standalone chips. So in this particular case, what you're looking at is a voltage sensor. Let me see if I can move this here. So this voltage sensor has two pads, one here and one down here. It has a bank of photovoltaics, a simple MOSFET transistor, and an LED to report the voltage between these two tabs, all right? So it's a very simple optically powered device that tells you what the difference between the voltage of these two tabs are. Now, if you look on the side here, there are two snap-off tabs. So if you're like me and you built airplane models as a kid, this would be the kind of plastic tabs that are holding your components to the overall scaffold. And you basically, to use the components, you have to break them off the tab. And same thing here. These are computer chips that essentially can be removed off the wafer. So these devices can now be taken off the silicon wafer and act as standalone little voltage meters, and they're very small. So let me show you what they look like in comparison to the kinds of things that people currently make. So on the left, I'm showing you the kinds of things that are made at the University of Michigan. This is called a Micromote. It's a computer chip that's about the size of Abe Lincoln's beard and on the penny here. Here from UC Berkeley, you're seeing smart dust, again, a very small computer chip. And for comparison, the devices that Al and Paul make are shown on the right here. And the reason you can't see anything, well, it turns out that on the penny, there are two Abraham Lincolns. So one of them is on the face of the penny. That's what's shown over here on the upper left. But there's a second Abe Lincoln. And if you look really close, he's located within the Lincoln Memorial. And so if you zoom up on that second Abe Lincoln, that's the chip that we're talking about. Right? Now, smaller doesn't necessarily mean better. In other words, these chips on the left have much greater functionality. They're packing many, many more transistors. But smaller does have the advantage that it becomes very cheap to manufacture. So these chips are quite expensive to make. These over here, because you can make so many of them on a wafer, are less than a penny a piece. And so there are lots of advantages to making small standalone devices. And in the very near future, you're going to see these as little tags. So look down at your finger. And if you notice that little speck of dust, that actually someday could be one of these little devices measuring the pH of your skin, or something that can report to a cell phone, you know, the conditions that are going on your surface. All right. So the electronics part, in terms of making machines at the small scale, that's basically a solved problem, especially with this ability to remove the electronics from the wafer. So what ends up being the harder piece is the mechanics. So why not just take a 3D machine and shrink it down to the micro scale? What's the problem with that? Well, it turns out that that's been tried. So for example, this is a turbine engine that was worked on by the Epstein Group at MIT. This was a decadal project, many millions of dollars spent, and it never really worked. And the reason it didn't work is that the physics that's governing the behavior of components really changes as you go from the macro scale to the micro scale. So there's a problem in the fabrication part, which is that, you know, you can't really shrink a graduate student down to the micro scale with a little screwdriver. So you've got to figure out how to make the machine differently. And the physics operating, the electrostatic attraction between surfaces, the fact that fluids become viscous on small length scales, all of that changes as you try to shrink your machines. And that really requires a paradigm shift in the way that we think about them and how to design them and build them at the micro scale. So we were quite inspired by this result that came out of Rob Wood and Eric Demaine's labs at Harvard and MIT respectively. And in this particular paper, what Rob and Eric showed was that you could take a sheet and essentially print an origami robot. Then you would slap a couple of batteries on, and once it folds its internal legs, it just walks off the page, right? So the idea here is to print the robots in 2D and now have them fold up into the third dimension, and then they're ready to go. Now, admittedly, 80% of these robots caught fire as they were, crawling off the page. But the idea of somehow printing in 2D is really quite inspirational. And the question now is, could origami enable machines at the microscale? And in particular, can we essentially steal all of the technology that's been developed by the semiconductor industry to fabricate computer chips? Could we now steal that technology to essentially fabricate our robots in 2D around these microchips, and then fold everything up and get it to adopt a 3D configuration that would allow it to function as the intended machine, right? So that is the idea. And what I'd like to tell you about next is sort of all of the things that went to make it happen, all right? So the first thing that I want to talk about is why origami. So origami is particularly attractive because these days we know a lot about the shape and the science of how it works. So for example, we can now make almost any arbitrary shape that you want out of a single sheet of paper. In fact, you can take a class at MIT that Eric Demain teaches on a program called Origamizer. That program essentially codes any three-dimensional shape, in this particular case, a model of a bunny, into a fold pattern. And it takes a while, so 8 hours by an origami expert, but once you've folded all of this up, you get the intended shape that you were going after. Here's another example from the Mahadevan group at Harvard, again, illustrating that by changing the fold patterns, you can really generate arbitrary curvatures and surfaces just by tuning or designing your fold pattern properly. So there's a lot that we know and understand about shape, and there's still ongoing research on trying to figure out how to create fold patterns that are universal, meaning that they could adopt more than one shape. And we're working on that, but this is kind of giving you a little bit of an idea of the types of things that, the flexibility that origami gives you. My group was quite invested in trying to figure out something about the mechanics of origami. And so the idea now is that origami, in addition to giving you shape, the fold patterns actually endow your paper with new material properties. And so it's, in essence, it makes your paper into a metamaterial where the stiffness of the material is really controlled by the fold pattern rather than the paper itself. Okay, so here's an example of one of these projects. This is called the Mura-Ori tessellation. And it's interesting because the pattern can fold into a flat shape. So the idea is that if you compress it, it'll fold into a flat state. And the fold pattern really gives you a stiffness to the pattern that's different from what's involved in the paper. I'm getting a little bit of a glitch, so I'm going to escape from this and try to do this again and see if that goes away. Okay, so now an example of the mechanics of this would be to try to measure the stiffness of that origami pattern. And that's indeed what we did. And we showed that if you introduce defects into the pattern, you can substantially change that stiffness. So in particular, if you take that same sheet and now you pop one of those valleys into a mountain, okay, so there is the pop through defect that we created right at the tip there. Now when you compress the sheet, it gets stuck once it gets to the defect. It becomes incompressible. Essentially, you've made the sheet stiffer by introducing a reversible deformation, because now I can pop that defect back, and now the sheet goes back into its original compressible state. And so what's interesting is that as a function of the density of these defects, you can essentially arbitrarily tune the stiffness of the sheet. And it goes like that until you start getting the defect density so high that these defects can actually interact with one another. So in this particular case, we're putting two defects, one up there and one down here. And what's interesting is that these defects have charge. And if you compress the sheet, they annihilate one another. And the sheet compresses as though there were no defect there. Essentially, what you've done is you've introduced a vacancy where those two vertices annihilate one another. And so again, there's a very beautiful interaction that you get between the charges on these defects, depending on where you place them on the sheet. So that's kind of an example of the mechanics that we're talking about. And we were able to show that by popping these defects in and out of these sheets, you could create patterns like pleats. So this is called a dislocation in crystallography, but maybe in the textile arts, you'd call this a pleat, where you have one row splitting into two. We could create rotations. So this is in physics, we'd call this a grain boundary, but essentially you're creating an angular difference between the pattern on this side versus that side. By popping the defects in and out along this spine, we could do it so that the spine was flexible and had a hinge-like behavior, or by making a different pattern of defects along that spine, you could make it rigid so that it could, it was essentially rigid to rotations about that hinge. And in fact, by calibrating the stiffness of these sheets, both when they're bare or when they have a single defect, we could then make predictions about the stiffness when we introduce 2, 3, or 4 defects, when we had the defects close to each other, when we annihilate the defects, etc. So all of this now made for programmable metamaterials, where all you had to do was pop the defects in and out in order to program the mechanics. Okay, so that's an example of the types of study of the mechanics of origami sheets. And this is just one example that we did in our group, but there are many others now, thousands of papers about the mechanics of origami that are just waiting to be tapped for anything that you want to understand about the mechanics of these folded structures. Now, at this point, this was our first foray into a brand new world of origami. And as often occurs when you make these giant leaps into the abyss, funny things happen. And if you'll indulge me, I'd like to tell you a little side story that, that took off from this particular science paper. So we were very excited to share our results, and we did so at the 6th meeting on origami in science, mathematics, and education. And what's really fun is the person there handing the baton off. So this person on the left here, that's actually Mura. This is the guy who the fold is named after. This is Mr. Mura. Ori means fold, so he is handing off the traditional origami baton to the next meeting organizer. And so that meant that we got to meet the Mura from the Mura Ori fold. And okay, so I didn't really get to meet him, but I did get to sit behind him. So this is the back of Mr. Mura's head. But my student Jesse, he got to meet him. So there's Jesse with Mr. Mura. Now we presented our results here, and around this time we got a little note, an email from an origami enthusiast in Israel, and he pointed out to us this painting of Lucrezia Panciatici by Bronzino from around 1540. And what's interesting about this painting is Lucrezia's yoke. And so if you're like me and have no idea what that means, the yoke is the part of the dress that's just surrounding the neck here. And if you look closely at her yoke, what you find is the Mura Ori fold. There it is. And in fact, in this yoke, you can see that they have something like a defect that allows you to go from a single pleat to now doubling the pattern, just like I showed you with our pleats. And what is interesting about this is that, Mr. Mura is old, but he's not that old, right? And this sort of points to the fact that many of these origami designs actually had some of their origins in the textile arts. And while Mura got the credit for the Mura Ori fold, clearly this type of pattern was already appreciated by the tailors back in 1540. And this got us thinking that maybe in the same way that the textile arts are contributing to the origami arts, maybe we can contribute back to the textile arts. And so this got us onto a part of my career that I call Science on the Runway. And it was really spearheaded by these two individuals, Win Nguyen, who was an intern working in our group, and Leah, who was a student in the department here at Cornell in the apparel department. And they ended up designing a whole line of origami clothing. So in particular, they took this pattern that my postdoc Bin Lu was studying, which is an interesting metamaterial that allows you to redirect forces away from this donut region. And they turned that into a dress. They pulled it up into the third dimension and pulled it into a dress. They took a design for a cylinder that had these pop-through rotations, as you can see here, and turned it into a purse. And with these designs, they essentially were invited to present at the Vancouver Fashion Week, which is a major fashion show that happens every year in Vancouver. They ran an Indiegogo campaign and were able to essentially raise enough money to go to Vancouver. And I was, boasting about this to my mother, and she said, "Well, are you going to go?" And I said, thought to myself, "Yeah, I've got to go to the fashion show where our origami designs are going to be presented." And so I also went, and it was spectacular. This is sort of what I saw. As a physicist, a fashion show is the last place where you'd think of finding yourself. Nevertheless, I thought that the things that I was observing there were really quite extraordinary in the conversations that they were starting. And these are just some of the other presenters that I thought were particularly interesting. And again, just very interesting conversations that I think they sparked by their designs. So this is what the scene looks like at a fashion show. If you're unfamiliar, basically you design your clothes, but you don't have the models in front of you. So you've got to tailor all of the clothes at the last minute to the models. And so Win and her brother brought up the sewing machine, and in the back rooms of the runway, you're basically fitting the models, sewing everything up, making sure that it looks good. And it's this frenetic activity. But in the end, they came up with this beautiful line of clothing that looked absolutely professional and wonderful. It was spectacular. There it was. And there was a particular purse that really had a standing ovation. So I want to show you what this looked like. So this was based on that cylinder design. And this is basically a purse that opens up or closes depending on how much stuff you have that you want to put in there. So this won a standing ovation. And again, really a tribute to Leah and Win for the amount of effort that they put in here. And I have to say that if you had told me as a starting professor that someday when you search origami fashion on Google, my designs would be on there, I would have thought you were crazy. But here they are on this search. So again, just a crazy story that came out when we just allowed ourselves the luxury that fortunately we have as faculty to essentially explore these kinds of ideas. Okay, so back to our original game plan. Remember, we're interested in the miniaturizations of machines, and we talked about the fact that origami gives you this ability to tune the shape and the mechanics of your materials. And the third property that origami really allows you to control is the scale. And the reason is that as long as you keep the thickness to length ratios constant in your systems, then basically any design that you make at the macro scale, so here a randlet bird with a scale bar of 20 millimeters can be reproduced at the micro scale. Same Randlet bird design, but now at the scale of 100 microns. And this is work that came out of Ryan Hayward's lab, where he folded these beautiful polymeric origami systems. So, so that's what allows you to essentially design things and then import that into the micro scale. So now an origami artist is only as good as their origami paper. And so if you want to build micro scale origami, you need micro scale paper. And at the time that we were thinking about this, again, my colleagues, Paul McEwen, David Muller, and Jiwon Park were doing these fun kirigami experiments with a single sheet of graphene. So this is what I mean by kirigami. It's when you take a piece of paper and make cuts in it. And here you're seeing a single sheet of graphene, a sheet of paper that is 1 atom thick being pulled and behaving the same way that that sheet of paper behaves under extension. And so since then, we've teamed up and really worked on designing other kinds of paper. In this particular case, Kyle, Tanner, and my student Barsh worked on building paper out of atomic layer deposition. This is essentially a technique where you spray paint a single layer of atoms at a time and bond them to one another to create sheets that are only nanometers thick nanometers in their thickness. And we could make these either contiguous, where in this particular case, the sheet is behaves very similar to a sheet of paper that you crumple up, or you could cut it up so that you could stretch it and then bring it back to its original conformation. But now it acts more like a kirigami sheet with cuts in it, kind of like what's being shown in this design over here. All right. So with this, we started thinking about how do we get the sheet of paper to actually start folding itself? Because of course you can make the sheet of paper, but if you don't have a micro origami artist, that's not going to help you very much to create the kinds of designs that we're interested in. We need to do something like what this video shows, which is to have the sheet of paper fold itself. And so this is an example of what we were able to create. This is work that was done by Mark Miskin, spearheaded by him, and then followed up by Qin-Kun and Wei. And essentially what we're doing is we're making a very thin sheet that can be electrically actuated to curl up on itself. And so this is really a breakthrough technology. And basically the way that it works, it operates, it's very low voltages, consumes very little power. It's very fast. It's basically rate limited by the surrounding fluid viscosity. It can work in aqueous suspensions that are compatible with cell media. And you can make it in the fab using the same tools that you use to make computer chips. And so this is the way it works. You take 7 nanometers of platinum and you cap it on one side with a titanium dioxide layer or some inert layer of graphene. You then pattern it and release the device. And when you put it in solution, if you put the platinum, if you apply a voltage to the platinum, then ions from the water in solution will absorb onto the platinum surface. And that'll create a stress that bends the platinum and causes the actuation. Once you put these panels, these rigid panels on, you can restrict that bending to occur in regions that you want to fold. And then that's how you get origami out. Okay, so that's the idea behind these actuators. Okay. Let me see, there's a question. Right. So just to give you some context on where this work sits in relation to the field, there's a lot of different ways that people have developed to actuate materials, but many of them occur at very high voltages, and that's not really useful for working in aqueous suspensions or for working with computer chips operated around a volt. And many of them operate at very low radii of curvature, which means that the bending is really quite minor. The work that I'm telling you about here, that's highlighted by this data point. And what you can see is that we're operating at pretty low voltages, about a volt, and we're getting very, very high, the highest radii of curvature of any device or any material that has been developed thus far. And the reason we want to get this sort of to this limit, the reason we want to push this limit is that if you're going to build a robot, you might use these materials over here. If you're going to build a milli-robot, you might be able to get away with using these materials. But if you're going to build something at the microscopic scale, you need something that can fold to less than a micron radii of diameter. And that's the regime that we're operating on here. So the device, the final device that you make can only be as big as the curvature or the radius of curvature characterizing the folds that you're making it out of. And so this really required us to push the material science into this realm. Okay, so being the new kid on the block gives you the ability to do all sorts of things that could never be done before. So now I'd like to tell you about some of the areas that we're pursuing. So for example, we're trying to make ciliated surfaces. So in your body, there are two modes of fluid transport, two primary modes. One is the pulmonary system that uses pressure to drive fluid through your arteries and capillaries. But the second is a ciliated surfaces, which essentially bring up the viscoelastic phlegm from your lungs and clear surfaces in the liver. And so this is basically achieved by having little hairs that pump the fluid across your surfaces. And we decided to try to see if we can make an engineered system that has similar functionality. So in particular, we made surfaces full of these cilia. So this is kind of what they look like when we actuate them. And this is what one of them looks like from the side. And you can see that the behavior is not exactly reciprocal, which means it doesn't just go back and forth. It executes this wavy-like pattern, which allows us to pump at this very small scale. So at small scales, fluids become viscous. They feel more like honey than water. And that means that you need to break symmetry in order to pump them. And indeed, when we actuate them at high enough frequencies, if you look very carefully, you can see these little tiny colloidal particles being transported by these ciliated surfaces. And that occurs because of this broken symmetry. Once you have the ability to transport, you can start designing different flow patterns. So for example, if each one of these little rows transports fluid in the direction along the orientation of the cilia, by putting these in special configurations, you can drive different shapes of the flows. So if you have all of the internal cilia activated, then all of the flows are going in to the square, and you essentially are creating what we call a sink. So fluid comes in, and then it comes out in the third dimension. If instead you actuate the outer ones, you can create a source. Or if you actuate these two surfaces, you create parallel transport. Or if you actuate these two in and those two out, you create a saddle geometry or a turning flow. And now you can put these elemental flow geometries together to achieve any design that you want. And so in particular, these are experimental images of these elemental flow geometries combined with simulations which show you what the particle trajectories look like in the third dimension. So the experiments are on the bottom. The simulations are depicted on the surface of this wedding cake with like a quarter cut out geometry, showing you the beautiful streamlines that these particles make as they are being pumped by the cilia. And so as I said, these can be put together. So in particular, you make these into an array, and with a little device like this, you can bond electrodes to each of these different arrays, and then use a pin connector to drive it with a computer. And so with this, you could, for example, choose to drive these particular cilia, creating a flow that turns and then drives the fluid in this direction. But in the other side of the device, you could have a completely different flow that drives the fluid up and back down. And both of these can be integrated on the same device and switch between each other. And so this is exactly what we did, and showed that you could essentially tune this array to create any arbitrary flow geometry, transport, circulation, splitting, and merging of these little streamlines, etc. Okay, so just an example of what we can do just with the actuators on their own. We're also pursuing this as a technology for deployable neural electrodes. So the idea here is that if you want to look at lateral regions in the brain, in other words, how do neurons over here correlate with firings of neurons somewhere else, one way you could do it is just by sticking basically ice picks in the brain in those two locations, but that ends up causing a lot of damage. So what would happen instead if we stuck a very thin fiber with a folded up pattern of these neural electrodes at the base of the fiber, and then put that in to the brain, and then unfurled the electrodes, kind of like the way that you unfurl a solar sail on a satellite. You put it in and then unfurl. And so this is something that we're pursuing with a group at Virginia Tech that's an expert in making these kinds of fibers. And to do this, we have to make sure that the electrodes can stay put once we unfurl them. And we can do that by driving a slightly higher voltage so that the ions that absorb onto the surface get embedded inside the platinum. Once that happens, there's a barrier for them to get out. And what you end up getting is something called a shape memory material, where you can essentially apply a voltage, remove that voltage, but the material remains in the folded state, and then it remains there until you apply the counter voltage to drive the ions out of the material and get the expanded state, right? So this ends up being a shape memory material that can hold its shape. And now you can do things like, have separate little electrodes that drive different parts of the pattern. You can even have a design where one electrode drives a hinge and a second electrode through a wire that passively goes through the first hinge actually ends up driving the second hinge, right? And that's what's shown in this video, where we initially actuate the first hinge and then keep it folded while we actuate the second hinge that goes, that's electrically connected to the first. And so this is how we want to do the voltage reading. We want to have a separate channel that goes through all of those activated hinges that only connects to the tip of the electrode and sends the current back about what that neuron is doing. We're making origami designs. So this is one of the designs that we made that graced the cover of Science Robotic this past March. The idea here is, again, to make designs where if we apply a voltage to them, you can get stages that move in the Z direction or can translate laterally, as you're seeing over here. They can hold their shape. And then when we apply the counter voltage to get the ions out of the platinum, they can be reset to their original positions. We can make origami patterns like this hexagonal fold, this Mura Ori, or this one, which is the world's smallest duck. And all we have to do is shift the voltage on and off in order to fold them, let them hold, or unfurl them. And that's the patterns that you achieve when you look at them under the SCM, as Qin Kun did. And now, really, I mean, what's amazing is that this type of complexity is achievable in a footprint that's only a couple of hair diameters big, right? It's really an amazing feat of engineering that Qin Kun and Wei and others have been able to achieve in the group. We're also transferring this ability to air. So the group of Nick Abbott and his postdoc, Nanchi, have been able to show that you can use the platinum to catalyze reactions in gases and create stresses that allow you to fold these structures in air as well. So that's coming online too. With Nick Abbott, Hadas Kreskazit, and Elisa Apsel, we're building metamaterials. So now we're thinking about these kinds of kirigami tessellated patterns that might allow us to make robotic sheets that can crawl up some chemical gradient and wrap it and fold around it. And so we've already shown that we can create hinges that allow you to create splay between two panels. So this is a fairly complicated fabrication procedure that allows us to make a mountain fold and two valley folds that, if you actuate, can essentially hide material into the third dimension and cause the splay of these two panels. And this is a confocal micrograph of one of these hinges in action, essentially splaying two of these hexagonal pleats. This is now 6 of them all working in concert. And you can see that as you go from the closed to the open structure, the area that's occupied by the structure changes. And that allows you to create Gaussian curvature. So in this particular case, we're showing you a sheet where the inside is being actuated while the outside is tethered to a boundary. And that allows you to create a dome-like shape. As the area of the inside expands, it has to pucker up into the third dimension. We're also working on wiring up the sheet so that the inside and outside can be activated independently through 2 wires that are shown down here. So when we actuate the inside, we get this very small dimple that pops out. Whereas when we actuate the outside, we get a saddle shape that you see here with 3 different minima that arise. And so you can do anything from actuating the outside, the inside, or both to essentially transverse between these kinds of designs in your metamaterial sheet. And finally, we're working on integrating electronics into these sheets to try to get the actuation to happen without external wires. So let me show you what we've been able to accomplish here. So the very simple idea is to essentially have silicon photovoltaics attached to these actuators, so that when you shine light on the silicon photovoltaics, the actuators can function. And so here's the very first movie that showed that this is possible. What you're seeing is a photovoltaic attached to one of these actuators. This is an SCM image, and this is what it looks like under the microscope. When we shine light, you can see the little arm moving just a little bit. This is our hello world. And of course, what we're interested in is moving from just this very sort of wave from the Queen into, you know, like something that you'd see at a rock concert. And so this is what we're sort of working towards. So you start getting ambitious. You put a photovoltaic for the front legs and a photovoltaic for the back legs, and then you make bajillions of them on a single wafer. You put on the pads These are now pads that restrict the motion just so that you get folding along here and here. And now you generate this device, which we lovingly call Brobot. Brobot likes to flex his muscles, that hair on his chest. The technical term for that is schmutz. And but you can see, he sort of belongs on a beach somewhere, flexing his arms. But obviously he has some defects. We're not really interested in the hairy part. His back legs have been ripped off. But it gives you an idea of the kinds of things that we could do. And these devices are very robust. You can pound on them with your electrode and they still work no problem. You can shine light from the back or the front and they work just the same. And if you work really hard to get the fabrication procedure just right, you can make this device. This is a 40 micron by 70 micron by 2 micron robot. You shine light on the front and then back photovoltaic to activate the front or the back legs. And by alternating where you shine the light, this robot folds itself up and walks off the Petri dish, a microscale analog to that macro scale robot that was developed in that Harvard and MIT group. This robot is so small that these little bits of dirt here that you're seeing are performing Brownian motion. That's the point where the fluid forces, the molecules that are bouncing up against them happen to bounce asymmetrically, kicking the particle into this random kind of Brownian motion, random walk. So this robot is right on the boundary of where that kind of behavior will occur. Immediately, you can see the potential for these robots. You could already put these basic payloads that Paul and Al have developed for voltmeters and thermometers and LEDs for communicating the state of the system onto these devices. In fact, if you had a 50 nanometer line width, you could essentially create an entire Intel 4004 chip onto this 10 micron by 10 micron footprint of these robots. That gives you a clock rate of about a gigabit per second. And for comparison, the Voyager 1, which just left our solar system, has an 8 kilobit per second clock rate. So it's an amazing amount of computational power that we're going to be able to put onto these devices. You're going to be able to put 60 megabits of memory on these devices for them to store information about what environments they've encountered. And there's a group of us at Cornell that are interested in things like little devices that we can implant in brains, microscopic robots that we can get to actuate, metamaterial robots, these robots which are based on bubbles that are driving them, and these little sensors. All of us are essentially working towards trying to integrate these types of electronics. And we're working with a company called XFab. This is a commercial foundry to do that. And let me just show you one example to finish off. This is a chip that we designed and then fabricated with this commercial foundry. And the goal of this chip was to essentially be a clock circuit. And what we could do with this clock circuit is drive locomotory gates in a robot. Now, instead of shining the laser on the front and back legs like a marionette where we're pulling the strings, this is the point where we cut those strings. All we do is power the device with photovoltaics and sunlight, and it walks on its own. And so this is AntBot. It has one of these chips that controls the legged locomotion. All we do is put AntBot under ambient light in the lab, and it walks on its own with this typical hexapod gait that you would see in an ant, for example, where you have two legs on one side and one leg on the other. that are on the ground at any one time. And then the other legs are moving to a new location. And then it switches between those two tripods to get the locomotion to happen. So this technology is here. We can now design ever more sophisticated brains to put on these actuators, really achieving the miniaturization of machines at these scales. We can suck these up using a syringe and inject them into various microenvironments, including one you see here, where a paramecium is going by our robot. You can release 10 million of these on a single wafer, each costing about a penny, able to lift 10 times their weight, and with the potential computational power greater than the spaceship Voyager. It really is an amazing technology platform that's coming our way. So what are we going to do? What could this technology enable at the 100 micron scale? Well, basically, all you have to do is think about what robots do for us at the macro scale, and now translate it to the micro scale. So we use robots to clean our floors. At the micro scale, these robots could be used to clean biological surfaces of, let's say, synthetic tissues that we're building. They can be used to assemble microscopic components. They could be used to transport cargo from one location to another, or organize their spaces. They could be used as surgical instruments that can be made, that can allow us to get to length scales 10 times to, or more smaller than what can currently be done with surgical robots. And they can be used to explore environments that cannot be reached by, optical microscopy, maybe cavities inside surfaces that we can't explore just by looking at them. Now, this journey that I've taken you on could not be achieved by any single group. It took an amazing cadre of students and faculty collaborators. And it's really due to this interdisciplinary collaborations across departments. What you're seeing here is ECE, chemical engineering, applied engineering physics, and robotics, all of which were important for catalyzing these efforts. And so with that, I'd like to thank the Cohen Group and Ching Kun, Barsh, and Wei in particular for their hard efforts to create the devices that I've shown you. I'm only reporting all of the beautiful things that they've done. And I'll be happy to take any questions.
Thank you so much, Itai. Absolutely incredible presentation. Are there questions from our audience? Feel free to either put it in the chat, or if you want to unmute yourself and just speak your question. Or if you want to raise your virtual hand.
Ask a question. Oh, Paul has a question.
Paul?
Go ahead, I'll follow you.
All right, I would like to know a little bit more about how the cross-disciplinary collaboration comes about, and like whether there are things that can help that sort of thing happen.
I think in some ways it's sort of natural on our campus. We have, or for some reason, attract the kind of faculty that, you go up and you say, hey, can you do this? And it's sort of, people are receptive to that. So that's the first thing. The second thing is that many of these collaborations are sparked by new initiatives. So in this particular case, the Mung Foundation provided us something like $5 million to try to come up with collaborations between faculty, in the realm of neuroscience. And so Al and Paul started thinking about, could we implant devices in people's brains that could then, through like essentially optical means, communicate what the state of the neurons are. And that's what led to these microscale brains that we essentially stole to try to make these robots. And the actuator part came out of interactions through the Cornell MRSEC, the Cornell CCMR, through an IRG collaboration, where we were looking at how to mechanically actuate 2D materials. And so really it's the ability of Cornell to foster these interactions where you get people into a single room to talk to one another and brainstorm about ideas that really they never would have done on their own. And then somehow have people that have enough fingers in different pies to recognize, hey, I could put this with this and create something completely new, like what we did here with the robotics, that I think drives the innovation. And I think that happens here on our campus, more frequently than not.
Thank you. Paul?
It really revolves around this, even an initial seed of funding to get people to share students and start to talk to each other was key.
Okay, so hi, Itai.
Paul.
The one question, it was sort of a random thought that came up. You mentioned at one point using these micro robots for cleaning tissues. And I was waiting for more applications when you were talking at the end of in situ, in other words, in the human body, since that, of course, is a subject of our colleague Paul McEwen's apocalyptic thrillers. But it wasn't there. And I'm actually curious if, and this is a sociological question, and I'm not joking, although it'll sound like it, whether it's something you're too sensitive about because, of all of the silliness about microchips embedded in SARS-CoV-2 vaccines and all that. And that was actually what I was thinking about when you showed us that beautiful picture of the chip on the fingertip.
Yes, so I should say we are thinking about putting these devices in the human body. Right now, the idea is to put them at the end of a little fiber that would essentially allow you to have, to thread it almost anywhere in the body through a capillary or an artery, and then have surgical tools on its end that would allow you to do the surgery. And the reason we do that is that it's very hard to get light into the body to power the devices. We would have to figure out a different way. If you wanted them to be untethered, you would have to figure out a different way to to power them. And we can do that maybe magnetically, maybe with a ratchet. We're thinking about batteries, but the initial idea is just to put them at the end of a fiber. And you're absolutely right. I'm totally pissed that Bill Gates is getting credit for the things that we're doing. And on a more serious note, I don't think that, I'm not worried about these microchips. First of all, I'm not worried about, the government tracking us using these microchips because they're already tracking us using, our phones. I mean, it's totally ridiculous. You don't have to use our technology to do that. And second, in terms of these microchips, running amok in our body, at the moment, they're pretty, we would be happy if we could get to a functionality that, even approaches a tenth of that science fiction type of behavior that Paul writes about. But yeah, thanks for your questions.